queries. Okay, thanks, Victor. This problem is under the big umbrella of something called combinatorial search, or what I like to call query access models. So there is a structure to which you have access to via certain subset of queries, and you want to use to learn something about that structure. So in particular, the question is just this. So there is a universe of n elements, and there is a partition of these n elements into k pieces, P1 to Pk, and you want to learn this partition. Okay, that's the question. So how do you access, what is the access you have? So we have in this for this what are called rank queries. So you can take any subset of this universe, and you'll get to know from this oracle how many different parts this subset hits. Okay. So if mathematically you want to go all I want to k with the k parts, and if there is some intersection, you get 1, otherwise you get 0. So that's what the problem is. And the question is how few queries or how many queries do you need to learn this partition? So that's the question. Good. So it will be, sorry? Yes, exactly. It is the rank of the underlying partition. Okay. So it's useful or more evocative to talk about colors, but they're not very visible from here. But the parts are, you can think of them as different colors: blue, red, green, black. And what this rank query is saying is how many colors are there in this subset. And you want to figure out all the color classes. Okay. So if you think for 30 seconds or something, you'll see that order n square queries is easy. Okay, so you can take every pair and ask them, are you of the same color or not? And if you go for every pair, then you can figure out all the classes. So n choose 2 queries is enough. If you think it a little harder, and for people here who teach undergrad algorithms, it's a good exercise to do. Yes. What do we want to find out, or what are we answering? We want to find out the color classes. We want to find the hidden partition. P1 to Pk. So K is not known, but tell me how do you find K in one query? You query everything, you'll get K. Okay. Other questions? So I should have mentioned you can ask any question, anything. And I'll try to repeat the question if you don't have the mind. Okay, so you can actually learn much better than n square in roughly n log n time by binary search. So how do you do this? So there are 2 steps. So one is first you want to find one element from each color class. Okay, so how will you do that? So you start with the first element, and that's of certain color. It's its own color. You look at the second element, and you query the rank of 1 and 2. If the answer is 2, then there are 2 different colors. If not, you throw the second element away. If you get a third element, you query the rank is 3, you get a third element from a different color, and so on and so forth. By doing one sort of n queries, scan the whole universe, you'll get one representative from each color class. Okay, so that's the first step, that's n queries. And after you've learned this basis, you can figure out where the other elements, what the color of every other element is by doing a binary search, right? So you have k fellows from each color class, you have a new fellow, you want to figure out its class. You take this element, take half of these elements and see if the rank of this together is the size of the set or not, whether the color is, if so, then I recurse on that, otherwise I recurse on the other half. So standard binary search, you take log n or log k queries for every element outside this basis, in n log k all you'll find everyone's color. Okay, so that's a nice exercise to give to your algorithm students. More importantly, if you think about this thing that I just mentioned rather hurriedly, we didn't really need the rank. We only asked if the rank of a certain subset is exactly equal to the set of vertices. We're asking if a subset of vertices have all different color elements. And that's, in the Matrix parlance, an independence query. So we're asking a much weaker query. In particular, this is a yes-no question. So this is a yes-no question. And even with this, order n log n query suffice to figure out the whole partition. So why we're stressing this, if you look at the problem from the other end of lower bound, what's the best you can do? Well, if you think about it, if I have k parts and there are n things, then there are roughly k to the n partitions. Every element has k choices. There are roughly k to the n partitions. And so if I take a partition at random, there are n the log of this number, roughly n log k bits of uncertainty in there, right? And if every query is giving you one bit, then you need to make log k, omega n log k queries to figure out the partition. So if you have only this query, whether the rank is equal to the set or not, you need to make n log k, so this is tight. But the rank query, which tells you the number of colors that set S has, this actually can range from 1 to, and it can give you potentially order log k bits of information every query. And so if you divide this n log k by log k, it's potentially possible that you can learn the partition in order n rank queries. Of course, not every query will do this, but this is not trivial, but this lower bound breaks. So the question that we started this work with is, can one actually design an order n rank query algorithm? Can you figure out this thing with only order n rank queries? And the answer that I hope to give you in the 20 minutes that I have is it is yes. Okay. So let me say a little bit why is this problem interesting? So it's a natural sounding problem. It's a toy problem. So, and in fact, that's one obvious question, curiosity. It also is a rank. So if you know what a partition method is, this is a question of learning a partition method using only rank queries. That's a natural question in the method optimization literature. The way he came up with this is actually the partition is the simplest hypergraph, one of the simplest hypergraphs. It's a hyper matching, if you so to speak, the things don't share vertices. And so this is the problem of learning a hyper matching, a matching in a hypergraph. And as I said in the beginning, this forms it's a problem lying in this area of combinatorial search, which includes something called group testing and all these things. So people have studied this in graphs, and sort of this is a relevant notion in hypergraphs. And I'm going to tell you a thing about graphs in 3 minutes. But the other why about we wrote this paper and I'm giving this talk is actually the primitive that is used to shave off this log k. So going from independence to rank, somehow have to use this log k has to be shaved off. It uses this thing called coin weighing problem. So this is from the 60s, but even though it's so old, I don't think many people know about it. So maybe the next 2 minutes I'll tell you about coin weighing, and maybe this will be the more important thing to take away from this lecture than the talk than the other things. So let me tell you what coin weighing problem is. So I'm going to shift here for a bit. So the problem is also in this query access model, combinatorial search. There's an n-bit Boolean vector. Okay, you want to learn this Boolean vector, and the access is you can take any subset, and you get to know how many ones are there in that set. Okay, so how many queries do you need to learn X? So again, if I do trivially, I can do it in n queries by querying all the singletons. But actually, you can do much better. Okay, and in fact, again, every query is giving you potentially log n bits of information. There are n bits of uncertainty. So n by log n is a lower bound. And what you can do is you can actually learn it in n by log n queries. And in fact, 2n by log n non-adaptive queries, which means I'll not change my queries dependent on previous answers. Alternatively, you can think of it there is a matrix, and so this is the unknown vector. There's an L cross N matrix where L is roughly 2n by log n. So that if you know Ax, you can learn X. You can figure out what X is. So this is a beautiful result. So this was known, this was problem studied by Sunderberg et al., but these constructions are due to Cantor, Mills, and Lindstrom. So these are things that are there. So you can actually shave off this log n that is out there. So is this clear? Is this? I'll not tell how it was done, but this is a primitive we'll be using. It is of that same ilk, but not. So it's going to use this uses the fact that X is Boolean, where compressed sensing X is not Boolean. Okay. No, this is not invertible at all. This is a very thin metric. So L cross N, L is much smaller. No, no, AX is not Boolean. AX is not an F2. AX have real numbers. Yes, computation is happening on. Yeah, good. So yeah, this does not imply that I'm not violating any principles of that. Good. Okay, so that's one thing. So you can basically shave off the log n there. The second point is a nice puzzle, which I maybe should have stated this one before the other one. So suppose you actually knew there was only one, like there's a Boolean vector and there's only one in that, and zero. Then same model, you can take any subset and you can figure out what it is. Then to figure this out, again you can do binary search. You can do binary search to figure this out. But actually don't need, like binary search is adaptive, but you can actually do this non-adaptively. So there's a log n by n matrix. In fact, the log n by n matrix is just the numbers 1 to n written in binary. And if I just look at any unknown vector with exactly 1 and the dot product of it, then wherever that 1 is, that green column is going to give you the signal of what that coordinate is. So you can do it in log n queries, non-adaptively. So you can find a single counterfeit point. So this is called the ones are the counterfeits. You can find a single counterfeit in just log n queries. Okay, where am I going? So let me show this problem. So this is a special case. So we want to learn a hypermatching, that's the partition learning. But if you just look at the graph case and you want to figure out a hidden matching, so there's this bipartite graph, you only know the bipartition, and there's a matching, dotted matching that you want to learn. And what queries do you have? Well, you have cut queries, but let's think of this as cross queries. So you can take a subset on the left, a subset on the right, S and T, and I will tell you how many edges go from S to T. So that's called a cross query. Something like very much like the graph cut query. And the goal is to reconstruct this matching. You can actually do this in 2n queries, 2n such cross queries. So I want to try to show this, how this works a little bit, just to underscore the use of these coin weighing problems, how they come up in this problem. So I want to learn this matching. So here is the view. So this is the view. So pick a vertex on the left. So from this perspective, it wants to learn one edge. There's exactly one edge that coming out of it, out of these n possible edges. And that's very much like learning one counterfeit coin among n coins. So there are log n, so it can make log n queries. So what is the query? It's going to take a subset Si on the right-hand side and ask you, hey, do I have an edge to you? And there are these S1 to S log n subsets. So if you know the answer, whether V has an edge to this Si, then I can, for this log n different subsets, then I can figure out where that edge exactly is. So that's what the single counterfeit finding is from one vertices perspective. And the key thing is that since it's non-adaptive, these sets S1 to S log n does not depend on the vertex. It's the same set for every vertex on the left. And therefore, if I want to know how many edges V has this Si and V prime has to Si and V double prime has to Si, if I shift my perspective to the right-hand side Si wants to know how many neighbors it has on the left. That is a coin weighing problem for each Si. It wants to learn this vector on the left, which has edges to this subset Si, and that takes 2n by log n. So 2n by log n, there are log n sets. If you multiply them together, you get 2n. Okay. So basically, as this is admittedly fast, but it's the same coin weighing strategy, once from the left, once from the right, and then you merge them together, you get this 2n. So that's the one that works for the hidden matching thing. Okay, so let's this was just a detour in some sense. We want to, before I finish my detour, let me tell you one other result which we'll need to use as a primitive. Suppose I want to find again the counter, I want to figure out this vector x, but I promised that there are at most v1s. So it's sort of 1, 1, n1s, and this is somewhere in between, there are at most v1s. Then I can get, so this is a sort of non-looking number, but the point is that it is what information theoretically is the lower bound, that is basically the upper bound, okay? So it's roughly d by log d times log n by d, but think of it as log n. So that many queries you can make to figure out the vector. Okay, so I'll repeat this again when I use it. What's the difference between the first thing is an existential result, but there is no efficient algorithm to decode it. It's also not clear how to find the matrix. The second one is that the decoding is efficient. But the efficient decoding leads to adaptive algorithms. Okay, so let's get back to the learning partition problems. What is the part? So people have taken them, so I can repeat the problem. There is a universe. The universe is partitioned into different colors, which we don't know, different parts. Given a set S, I can figure out how many, all I get to know is how many colors are there in that set, and I want to learn the partition. So the algorithm goes to see as follows. I'm going to always maintain a collection of independent sets. What is an independent set? An independent set is a set which does not repeat colors. Okay, so I want to IT. Initially, it is going to be just singletons. So I have every singleton its own ITs. And then I'm going to put things and merge. So I'm going to keep two independent sets, merge them. And as I merge them, I might repeat colors. But when I repeat colors, I remember, I throw a repetition out, but I remember who was it that threw me out. Okay, and we'll keep doing that. So that's the idea. So let me describe what the merge process is in a little detail. So it's going to take two independent sets, I1 and I2. So they look like this. There are three different colors there. I've written similar size because that's what we're going to do. We're going to make sure that we always merge two similar sized independent sets. And the output should be this. So this is I3. So it contains all of I1 and one black item from I2. And then it remembers that the blue item from I2 has this parent who is the blue item from I1, and the green item from I2 has a parent from green item. So that's what the output of merge should be. Okay. Now, if you have this, the full algorithm is the following. I initialize with these singletons. I maintain independent sets in sizes of buckets of powers of 2 buckets. In a bucket where every thing is roughly the same size, I keep merging them. And when I merge them, the resultant independent set might go in size, in which case it will go to the next bucket. And I keep doing this till I have one independent set left in every bucket, and then I just merge them sequentially. So that's the whole idea. And after I finished all this merging, there is one independent set. Those are the representatives of each color. But everyone else has a edge to somebody who kicked them out. And I change these edges and I find the whole partition. Okay, so this part is, it's first share it might be a little too much, but it's really simple. So let me, how much time do I have? 10 minutes? Roughly, okay. 1 plus minus epsilon. So let me try to tell you how to merge and how much does it cost. So what is merge? I have two independent sets of roughly the same weight, and I want to figure out this sort of structure. And remember, I don't know their colors at all. Okay, all I know is that each independent set has colors of all different colors. So the step one here is to figure out who are the common elements. So step one is on the left. I want to figure out which elements, like in this case, the first and third element, have colors that are shared by some other elements in the second independent set. Again, I don't know their colors. Okay. So this is, you can do it as follows. You can think of it as a vector I'm trying to figure out. So X is a t-dimensional vector where t is the number of elements in I1, where I1, if that element has a similar colored element in I2. Okay, so this vector here is 1, 0, 1 that I'm trying to learn. Now, note if I take any subset of elements on the left, and I want to know how many of these ones are there, that can be, so what is that? How many of the, in a subset on the left, how many of the colors are shared by people on the right? Well, that can be with two rank queries, actually just one rank query. I figure out the rank of that subset I2, I join them together and I figure out, so the number of how much this increases by, actually maybe there's a typo here, the increase is actually the new colors in S that are not in I2, and if I have one which is common, I should subtract it. So this is, so basically it's, this is a typo, but the point is that using just the rank of C1 I2 and rank of I2, I can figure out how many elements in S, the subset S, share a color with someone in I2. In sum, I can figure out the number of ones in S in just order 1 rank queries. And therefore, I can learn S, right, using the coin weighing things, in order, I can learn X in order S log 2 by log S, where what is S? S is the number of common elements. Okay. This number could be 1, or 0 even, and this number could be as high as t. I don't know, but it's something like this. And once I learn this, who are the common elements, the step 2 is learning the matching among the common elements. But that's exactly the learning hidden matching thing. So I will skip this a bit, and I just believe me that this also can be learned in order S time. Okay. So in particular, to summarize, if I have two independent sets I1 and I2, and they're of roughly the same size, and the size is I'm calling P, which is some power of 2. And S is the number of common elements, which I don't know yet. S has a range. Then merging can be done in roughly S log T by log S. Okay. S log T by log S. Okay. That's one merge. I'm going to do many merges, and overall I want order N. So how does that happen? Well, let's say analysis. It's an analysis trick. So let me show that, and then I can maybe conclude. There are two cases: S is large and S is small. If S is large, how large? This is roughly some polynomial in T. S is bigger than square root T. Well, then log S and log T are the same order. Okay, so log T and log S are in the same order. So in that order, S log T by log S, log T and log S will go away. I will pay order S. But I'm also finding S common elements, and these common elements will never bother me again. So I can charge this order S cost order 1 on these common elements. So I'm paying order 1, and I'm happy because I ultimately I want to pay only order N. The issue is, a slight issue is when S is small. T is large, but S is small. In which case, I might pay log T, but T could be as large as N, log N element that I'm going to discard and never consider again. So just this is going to give us order N log N. So we need to amortize a bit. And amortization is, the observation is just this as follows, that in this case, when S is small, so the number of common elements is small. So I'm merging I1 and I2, but really there are no many common items. Maybe S is 0, so there are nothing in common. But in that case, the resultant I3, like when I join them, I have an I3, which is another independent set, and then I have some common elements. That size has increased substantially. It's not double, but gone up by some 1.9 times. So in particular, this I3 will go to the next bucket. Okay, maybe not in one time, but in the second time, will go to the next bucket. And if it goes to the next bucket, what it means that at the Tth level, if I consider this buckets of where independent sets of size T, mergers of this form where S is small, there cannot be more than N by T. There are N elements in all, everything is size T, the number of such mergers is N by T. So for these N by T, I'm going to pay this S log T by S. So let's see what happens. So this is a little bit of math. So I have N by T. I'm not even going to try pointing. There are N by T such mergers. Each merges takes S log T by log S. But S is small. S is at most root T. So I have N by T times root T by log root T times log T. But log T and log root T will cancel. Root T by T, I have like N by root T I pay. So I pay for the mergers of this phase T roughly N by root T. But there are two rows. So as I'm going to pay N by root T for all T. So this is going to be summation T N by root T. But except that T's are powers of 2. So I'm paying N by root T, but T's are powers of 2. So this is a geometric sum, and I pay order N. So that's it. That's the whole almost the whole algorithm analysis for this problem. Again, the thing that I want to sort of maybe you to take away is that these coin weighing things, the coin weighing problem really forms the heart of this algorithm, and it actually forms the heart of many such algorithms that have been going on in the last few years. How much time? Okay, good. So then let me tell you some problem that we could not solve, and this is then we tried hard. Okay, so this is the conclusion. So this was the first slide. I have a universe of N elements. I have this partition matroid rank query. We can learn in order rank N queries. But suppose I change the problem where this 1 becomes a 2. Okay, so this is now a generally partition matroid. So there is a partition, and when I query a subset, if you know partition matroid, then this is just the rank function of a partition matroid where the capacity of every part is now 2. But sort of just to get an understanding, I take a subset S. If I go to every part, And if I get nothing, I get 0. If I have one thing, I get 1. If I have two things, I get 2. And if anything more, I get 2. So every part is giving me 2, 0, or 1. And so a total rank of this will be between of a rank of S between 0 and 2k. If I just change that 1 to 2, can I learn this P in order n queries? And we don't know. The best we could do is we could learn in n plus k log k queries. So if k is small, k is less than n by log n, then we can learn it. Otherwise, we can't. And I'll tell you what the bottleneck is. The bottleneck is finding one element from each part. Because if you can find one element from each part, then you can learn it rest in order n. But somehow we don't know how to learn one element in each part, except by doing a binary search kind of idea, which does not exploit the rankness, or we don't know how to use that. We don't know how to put in point weighing in that. And the reason is point weighing is actually a linear thing, and you're getting a linear, like it was a matrix. And this rank is not linear in some sense. So we don't know, that's why we're stuck with, and if any of you can solve it, I would be, as in, please let me know. So let me conclude. So the take home points is you look at a natural partition finding question. I think it's a cute thing. We do roughly 9 queries, but the lower bound is still n. You could think about what's the right coefficient of n, but I don't know if that is a prudent thing to do, but it's still open. But the main thing again is that these coin weighing algorithms, you don't know about them. These are very cool. So that's something to put in your arsenal. More generally, this is a simple case, as I said, of hypergraph connectivity. So I give you a hypergraph. So this is just a general question, general hypergraph, and you have just cut queries. So I can take a subset and ask, I'll tell you how many hyper edges cross it. What is the fewest such cut queries you need to figure out that the hypergraph is connected? How many such queries you need to find the minimum cut in hypergraph? And more generally, what's the query complexity of submodel function minimization? That's something that have been open for a while, and I don't know the answers to this. So with these, I will end. Thank you.
Questions. Unfortunately, there are no brownie points for the speaker. So any question? So I just wanted to know, so the way you study in terms of the matrix, that we are trying to find matrix A, so that AX is a unique identifier what the X is. Is it able to see what the random matrix A works?
Yes. Random matrix A works. As in not, I don't know about the easy to see, but yeah, it's just you can do it with the using the browser.
So what we change it to 2 from the last, like this open problem.
So this was the problem we looked at, and here it was 1. So every part, so when you take a subset S, if I ask you how many colors it hits, I'm basically going over every color class, and I'm saying, did you hit anybody or not? But this is more nuance. It's saying, if you hit nobody, you get 0. If you hit 1% of the color class, you get 1. If you had 2% of the color class, you get 2. But if you hit 3% of the same color class, you get 2.
So that's missed information.
It's so what did you say?
Some sort of information.
Yeah, it's some sort of multiple, but it's capped at 2. And this sort of, I don't know how to quickly find one element from each.
And can we still this also in the matrix form? Like just
the matrix form was for the point weighing problem. So
okay.
So we don't know how to import the point weighing techniques here.
So that's not a very natural randomized algorithm.
Yeah, I don't know of any natural randomized or I don't know of a natural of an existence proof either for this. This becomes more complicated. Yeah. Yeah, I should have mentioned that. Yeah.
So in the point weighing problem, suppose you also have a constraint on how many points you can have in the natural constraint, because suppose you cannot weigh as many points as you want. Suppose you can only make 8 points.
Yeah.
Then what is the bound?
I don't know off the top of my head. Yeah. So you're saying when the weights are constrained.
Yes.
Yeah, I don't know off the top of my head. It's a natural question, but I don't know the answer.
Yeah, so
Yes, also obvious impossibility results. As inefficiently, right? Yeah, so now, so yeah, even a laminar matroid, you can, with two sets, you'll never be able to find the inner set unless you make exponentially many queries. So because you've, yeah.
Thanks.
any more question? Okay,
Yes.
so one last question. So here.
In the coin-weighing problem, is there an explicit matrix as well?
Yes.
We have that for the 2n by log n.
Yes, yes, it's an explicit matrix. Okay, there are two different explicit matrices from 66, Cantor-Mills and Lindstrom. Yeah.
Okay, thank you.
So, Deepak, you also mentioned like something about the hypergraph connectivity problem.
Yeah.
So, like, what's the current best bound known?
So you can figure out if a hypergraph is connected, just connected in n log n,
I see.
and we don't know of any lower bound. Hypergraph, if you want to find the minimum cut, I think the best is to think of it as submodal function minimization, in which case it's roughly n square. So that's
And the queries are like, I specify some subset, how many edges.
how many hyper edges are split by this thing.
Thank you.
Okay, so let's thank. The time in we switch, let me actually brownie question. So so what the key is to solve this problem with this ongoing problem? So what is the number of queries that is required to solve that problem that actually he mentioned? Do you remember the number of queries? Exactly. Not in all terms, even like no specific.
One plus little y divided by
Okay.
one.
Okay, so we you can note down the name. So our next speaker is so we have to. Do you know where is that?
Soon.
Something. This is the next one. Okay. Point. Yeah. So the space and then. This is next. This is previous.
Okay.
So, this session will be Rishikesh who talked about some new results of the.
Hello, I'm Rishikesh Gajala. I'm a PhD student at ISC. I'll also be on the postdoc market soon. This joined up with my advisor Sunil, who is at ISC. Seven, who is an undergrad at ISC and now moved to University of Birmingham for his PhD. And Rahul. So there are two main takeaways from this talk. The first is connecting the popular longest processing time heuristic to maintaining lower envelopes from computational geometry to seemingly different things, and using this with linear time LPT implementation. And the second result is that we prove that this LPT heuristic is indeed very good to a natural drone-based delivery problem. And we prove that this gives a 1.62 approximation, which is the golden ratio. Okay. So there are a lot of vehicle routing problems which are being studied in the operations research community. And Rahul was talking to someone called John Carlson, and he introduced Rahul to problems with trucks, drones, and a lot of things. The high-level kind of problems they look at is what is the optimal set of routes one has to decide for a fleet of vehicles, so that you traverse and deliver all the parcels to a given set of customers. So maybe 50 years ago, they started studying this with trucks. If you study the problem with a single truck, this is the traveling salesman problem. Then there are variants where people studied with multiple trucks. And after that, maybe 20, 30 years ago, people started looking at trucks plus drones from a warehouse. And now people started looking at problems where you only have a warehouse and a lot of drones, because that's being used in most of the places already. Mathematically, roughly the problem is the following. You are given you have a warehouse which has n drones. Let's denote each of them with a DJ. And each drone has some speed Vj, and it has a battery life Dj. So by battery life, we mean that the drone can do a round trip distance of at least Dj. It can come back to the warehouse and it can be charged. And you have n parcels, and each parcel is delivered at a distance Li by 2 from the warehouse. So if you want a drone DI to deliver a parcel PJ, it should have the battery life good enough to traverse this distance and come back. That is, Li should be at most BJ. And the delivery time one a drone would take for each parcel would be Li by BJ. Now the goal is to minimize the next time of this problem. Let's see a simple example so that it sinks in. Let's say you have two drones, and one of the drones has a speed of 60 kilometers per hour, and other drone has 20-kilometer coverage. And the second drone, it could have a speed of 30 kilometers per hour, which is slightly slower and a higher coverage. Let's say I have 5 parcels which are at distance 10, 15, 20, 20, and 30. One kind of allocation could be that the parcel which is at 30 kilometers can only covered by drone 2. So let me just assign it to drone 2. And the remaining parcel, I could assign it to drone 1. And since drone 1 has to cover a total distance of 65 kilometers, has a speed of 60 kilometers per hour, drone 1 would take 65 minutes. And drone 2 has to do only one parcel, which is at 30 kilometers. And if it's 30 kilometers per hour, it would take 60 minutes. So the next plan for the allocation 1 would be 65 minutes. Similarly, you can increase the number of parcels and get a different allocation. And let's say if you allocate cell 5 to drone 1, since it's outside the coverage, this is invalid. So this is the problem I got in my comprehensive exam. He gave me like, if there are 2 drones, how do you solve this problem? Like, what are the optimal things? And I was able to do that. Then he continued and said, let's look at this more general problem and what can we do about it. We started thinking about it and I was tossing ideas. Then he said that even I don't know the answer. And that's how we started working on this problem. There is this simple algorithm called the longest processing time algorithm. And turns out this algorithm is very good for this particular problem. Let's see what the simple heuristic is. So we take all the parcels first and sort them in the decreasing order of distance. So we have these 5 parcels at sorted distances. Now you assign each parcel greedily and minimize the current load. So first, when you take the parcel 5, which is at the largest distance, you know that it has 2 options. It can go to D1 or D2. If it goes to D1, it doesn't have enough coverage. So by default, it should have gone to the second one. And that would take 80 minutes. Now, for the second parcel, it has enough coverage to do both drone 1 and drone 2. Had it gone to drone 1, it would take 30 minutes. Drone 2 already had an 80-minute job, and this is another 60 minutes, so it would take 140 minutes. So if you keep minimizing it greedily, you should have assigned this to drone one, and you keep doing this repeatedly, and you get an allocation. And turns out this allocation is decent, and most of the things, this algorithm has been there for 40 years, 30 years, I don't know. And a lot of people have studied even it in practice. And for most of the problems in operations research, this is a really good algorithm. And even though there are more general problems and special cases of problems. So consider the drone problem I just talked about with infinite coverage. There is no battery life at all. Every drone can deliver any parcel. Then this is the classical uniform scheduling problem. And even the uniform scheduling problem, if you have all velocities to be same or the speeds, and you get the identical scheduling problem. All these problems have p-TASes, but still most of the people, researchers in operations research use LPT in practice. And that sort of that makes theory people also understand like the simple algorithm, what is the exact approximation ratio. Like even though there are better algorithms which work well in theory, but not in practice. So for the identical scheduling problem, it is known that this algorithm, this heuristic have an exact approximation ratio of 4/3. But the uniform scheduling problem, there is a long line of papers, maybe 5, 6 papers. And after those, the current best known bounds for LPT are a lower bound of 1.54 and an upper bound of 1.58 for the approximation ratio. And since uniform scheduling problem is a special case of the drone problem, you know that the lower bound of 1.54 also holds here. And we know that there is an upper bound of 5, which is roughly 1.62 for this problem. There are more general versions which people also study, like the uniform scheduling problem with constraints. And for those, the LPT algorithm is worse. Like you could see that the approximation ratio is at least 2 every time. And the most general problem in scheduling is the unrelated scheduling problem where LPT is not valid at all. So let's first look at the first take about LPT algorithm. The LPT algorithm has been heavily studied, like I said earlier. A lot of people study the LPT algorithm for uniform scheduling problem, but turns out all known implementations of LPT algorithm, even for this very well studied problem, take quadratic time. And it's surprising that there is no near linear time algorithm not known for it so far. So we give a nice connection between this LPT algorithm and something called lower envelope, which I'll get into in a minute. So the way LPT algorithm functions, that each job J with length Lj, you have to pick a machine I for which the term the current load Ti plus Lj plus Vi, that is the time taken for this new extra parcel to be delivered, is minimized. If you look at it closely, this corresponds to the line x by yi plus ti, where x is nothing but Lj. So you can think of each drone corresponding to a line, and this line is somehow changing each way, and you somehow have to maintain something to do with this. Let's see what we have to do. So let's see what lower envelope is first. Let's say if you have many lines, then lower envelope, in a lower envelope, one has to maintain the minimum at pointwise minimum over every point in the x-axis. So if you take the line L1 and L2, you know that initially the line L2 dominated and is minimum throughout, and later L1 is minimum throughout. And let's say if you introduce a new line L2, L3, you know that L3 is smaller in the initial parts. You could also introduce one more line and you get your lower envelope keeps changing. And from a recent result, it's known that there is a way to dynamically maintain this lower envelope. And one can either insert or delete lines with at most log square m time, where n is the number of lines. And you can also query the minimum point with order log m time. Now, using this data structure, we know that each of the LPT heuristic can be seen as a line segment, line. And one can use this and get an LPT algorithms implementation in order n plus m log square n plus log n time. And this is for the classical uniform scheduling problem. Even for a variation of the drone warehouse problem, we can make this work with little more work. And yeah, this is the first linear time LPT algorithm. Now we'll get to the second result, which is the fee approximation. The high-level sketch of the fee approximation is the following. We start with a minimal counter example where the approximation ratio is greater than 5. Suppose now this is towards a contradiction, and whenever we find something structure about it which contradicts with itself, we can prove that no such counter example exists, and that would be sufficient to show that the ratio is at most 5. First, let's look at normalized things so that things get much more convenient to us to deal with. So for all instances, we can assume that the size of the last parcel is 1. This is by simply scaling the sizes of all parcels. And secondly, we can also scale the velocities so that the total time of the opt is exactly 1. We don't exactly know opt, but this is just for the sake of analysis. So when we are writing the algorithm, we never have to know what opt is. Now, there is some value of opt, and for analysis sake, let's just scale it so that we get this. Now let's see what the minimal counter example I talked about is. So consider all the instances where the approximation ratio is greater than 5. We have some instance I. It should have been the case that the time taken by our algorithm is greater than 5 times whatever the optimal algorithm can do. Now, among all such instances, I want to pick the instance with as few jobs as possible. And because of this is the smallest instance, that is the minimal counter example, consider any in the sequence of doing these jobs, we need the last job ln. You know that all the jobs should have been done before the 5. Why? Had it been more than 5, you have a smaller counter example, and that contradicts of the minimality of what we had for this. So using the structure of minimal counter example and the simple scaling with it, let's look at 2 small observations. First is that, let's say the total load of the drone I for the algorithm, excluding the last parcel, is LIF alg. I want to say that this LIF alg is recently big. How do I do that? I know that had I added the last parcel, which was size exactly to 1, to any of the drones, then it should have exceeded 5 times whatever is the optimal. Otherwise, I would have given assigned it to that in the beginning. So we know that LIF all plus 1 is at least by VI is at least 5. And by just rearranging the terms, you get that LIF all is at least 5 times VI minus 1. And we also know that the total time taken by opt is at most 1 for each drones by the scaling we did earlier. So we know that LIF opt is also at most VI. So we have a red observation which says LIF all is recently large. We have a blue observation which says LIF opt is somewhat small. And we also know that the total load in all plus the last parcel Pn of size 1 is equal to LIF opt. So you have some things which should be large each time, and the LIF opt which is small each time, and we somehow have to get a contradiction around this. And for this, we discretize the distances. That is, we split the jobs into 3 types: small, medium, and large. And small jobs are the jobs which are of the size 1 to 5. Medium jobs are of the size 5 to 2, and the large jobs are 2 or larger. And for all the small jobs, we discretize it to 1. For the medium jobs, we do it to 1.5. And for the large jobs, we use the greatest integer function. The analysis using this rounding takes quite a bit of time. So I will tell a much oversimplified version where I discretize things to integers. And since we are discussing integers, let's look at a much more relaxed condition for now. That earlier we had the observation that LF always at least 5 vi minus 1. Let's look at a much weaker relaxed condition of Li always greater than vi minus 1. And we have the stronger discretization of only integers. And we also had earlier that Li of opt is at most vi. And now it's easy to a simple contradiction here that suppose Li of opt is less than Li of alt for some. We want to get a contradiction now by assuming the contrary. So if Li of opt is greater than Li of alt, we know that since these are discrete distances which are integers, Li of opt should be greater than or equal to Li of alt plus 1 because all the loads are integers now. And we know that from the earlier red observation, Li of alt plus 1 is at most vi minus 1 plus 1, which is vi. And the fact that Li of opt is greater than vi contradicts our blue observation. And this concludes that Li of opt is less than Li of alt for all drones. Now we can just sum up these quantity over all drones, and we get summation of Li of opt is at most summation of Li of alt. And we know that except for the last load, everything in Li of alt was also in Li of opt. So we know that sum of Li of opt is at most is exactly sum of Li of alt plus 1. This contradicts the inequality we have above. That completes the proof, and we know that no counterexample exists with approximation ratio greater than 5. So the approximation ratio is at most 5 every time. There are some open problems. First is there is a log square term LPT runtime. Can we improve that and get like an exact answer? We know that there is a lower bound due to sorting, which is simple. And there is also in the approximation ratio, we obtained a 1.62 upper bound, and the lower bound is 1.54 which comes from a much weaker problem of uniform scheduling. Can we narrow the gap between that? And we also there are also a lot of problems where we can consider multiple warehouses, mix of drones and types, recharge time, and other factors. So the high level, we combined the scheduling heuristic, which is very commonly used in the operation research community, with geometric data structures to get a near linear time algorithm. Then we also found that this LPT algorithm extends to a more complex setting of drone warehouse problem, and obtained a fee approximation algorithm for this heuristic. And there are plenty of open problems in more complex vehicle routing. Thank you.
Any questions, Srikar? So, sample books of drones according to the battery series. So, what is that case?
I think that would go to the uniform scheduling problem with constraints.
I see.
So here you have more structure that in these problems, let's say there is a hierarchy, like if certain, like it has a higher battery life, it can do like a continuous sequence of parcels. If that is not there, that goes to the more general problem of USPC sort of problem, where we know that LPT is not as good. And the exact ratio is also not known. It's not,
But is a constant one?
it's not known.
And what's the last one? The unrelated?
Unrelated scheduling problem is so that you can't even say here you have that the time taken is Li by Vi. UN don't have that, like it's a function which.
I see. Okay, thank you. Any more question? Can you go to the last slide?
Yeah.
In the open question. No, so one slide before. So your first, no, next one. So this, yeah. So what is the current based runtime? It is this, and that is the, okay, I see. So you want to just shape that extra bucket. I see. Okay, so if there are no more questions, so then let's thank the speaker again. And simple question is like, what is the best approximation ratio for this identical scheduling problem? Okay. So